Hi everyone, this is Lab 1.4, determining the relationship between absorbance and concentration for a solution. So for this lab, it actually is going to be done in two parts. The first purpose, or our first part, is to determine the relationship between absorbance and concentration for a blue food dye solution. So what I have here is a known solution. This is known as our stock solution of blue food dye. So all that is inside of this bottle is deionized water and blue food dye. Now, our first task is going to be to determine the relationship between the absorbance of this solution and the concentration. We can then utilize that information that we determined in part one of the lab to then analyze a Gatorade solution to determine the mass of blue food dye in this Gatorade solution. So how are we going to go about doing this? Well, I am going to need to dilute my stock solution to different known concentrations and then measure the absorbance of the various known concentrations. So what I'm doing in the first part of this lab, I'm changing the concentration on purpose, and I'm going to measure the absorbance. This is going to allow us, or allow me, to determine the relationship between concentration and absorbance for blue food dye. Now, before we get started, we have to determine the concentrations that we are going to produce. And the lab itself tells you, hey, your first test tube or your first solution is going to have 0 milliliters of water and 10 milliliters of stock. The stock solution is 7 times 10 to the negative 6 molar. So if we have 0 milliliters of water and 10 milliliters of stock, our concentration will be that of the stock solution. It will be identical because we have yet to dilute it. Now, in our second example, it tells us to use 8 milliliters of stock and 2 milliliters of water solution. So I am going to be diluting this solution by adding 2 milliliters of water to 8 milliliters of the actual stock solution. Well, how is that going to impact the concentration? Concentration is a measure of the amount of moles of solute per liter of solvent. If we increase the volume, if we increase the solvent, we are then thus decreasing the concentration. Let's take a look at how that looks mathematically. So, what are we starting with? We are starting with a concentration of stock solution of 7 times 10 to the negative 6 molar, or moles per liter. The volume of stock solution that we are using is 8 milliliters, or 0.008 liters. We don't know what the new concentration is after we dilute this. So that's what we're solving for. And I know that the final volume of the solution, if I use 8 milliliters of stock and 2 milliliters of water, the total volume after I dilute will be 10 milliliters, or 0.01 liters. Quick calculation here. 7 times 10 to the negative 6 is 0.008 divided by 0.01. M2 is equal to 5.6 times 10 to the negative 6 molar. So we expected this to go down because we were diluting our solution. We expected the concentration to go down, and it did. So what do we see here? This is 5.6 micromolar, or 5.6 times 10 to the negative 6th molar. Go ahead, pause the video, and see if you can figure out the remaining concentrations of our known solutions. after crunching through all of the calculations, you should see that the following concentrations will exist after our dilutions. So with 4 milliliters of water and 6 milliliters of stock, we will see a concentration of 4.2 micromolar. Moving down the line, we have 2.8 micromolar, 2.1 micromolar, 1.4 micromolar, and 0.7 micromolar. And I was able to determine all of those concentrations by simply using the same dilution equation. So at this point, we are ready to get a jump start on our lab. You can see the data table here is empty because in the beginning, I did not know the concentrations that we would be using. So what I'm going to do is I'm just going to fill out my concentrations in this data table over here, and then we'll get to making the solutions. So I'm just going to label that all of these are in micromolar. So I can simply say this is going to be 7.0, 5.6, 4.2, 2.8, 2.1, 1.4, and 0.7. So now, what I'm going to have to do here is make all of these solutions, and then using a device known as a colorimeter, and I'll zoom in on this when we actually get to this part of the lab, if putting a solution inside of this device then allows us to read the absorbance using another device known as the Vernier probe. So with that being said, when we get to the actual part of the lab here where we are measuring the absorbance, I'll move the camera so you can kind of see what that looks like a little bit better. Now, in order to have specific volumes, you can see here we need specific volumes of water and stock. What I'm going to do is I'm going to use a device known as a volumetric pipette. So you can see here, here's a pipette, volumetric pipette with a pipette bulb. It's a little bit different. If I move up, see here, this will allow me to get exact volumes of liquids going from 0 to 10 milliliters. So this is going to be more accurate than simply using a graduated cylinder. So what am I going to do? Well, I am going to have one beaker filled with stock solution. I'm only going to be using about 50 milliliters of stock, so I don't need to use too much. I'm not going to pour too much there. And one beaker filled with deionized water. Before I get started, I want to make sure that my beaker that I'm using for stock solution, as well as the volumetric pipette that I'm using for my stock solution, is isolated. My water, my deionized water, is also isolated on the other side. The reason why I want to do this is I do not want to mix up the two volumetric pipettes in terms of what I am using. The whole point of this first part of the lab is to keep the concentration at a known value. So if I mix up the stock solution volumetric pipette is with the deionized water, I'll be throwing off the concentration. So before I get started here, I want to coat the inside of my volumetric pipette with stock solution. So you can see, hopefully see the stock solution rising in the volumetric pipette. Now what I'm doing here is I'm just letting it sit. I'm actually going to empty this down the drain. What I'm trying to do is coat the inside of the volumetric pipette with stock solution to ensure that if there was any water in here or any sort of contaminant, I am rinsing it out, and all we are going to have is our stock solution. So, rinse this out. I'm going to do the same thing with my deionized water. Takes a little bit to empty with these things. going to do the same thing with my deionized water. Once again, I want to ensure that I'm rinsing out any contaminants, and the only thing inside of the volumetric pipette is, in fact, the liquid or the solution that we want. This one's a little bit harder to see because it is a clear liquid. What I'm going to do now is let this rinse out to ensure, once again, that all we have inside of our pipettes are either deionized water or stock solution. Okay, at this point, I am going to start to make our solutions on our table here. And when you are all in a lab, this is a technique that you can use. What I've done here is I have labeled water and stock solution. You can see my first test tube there is 0 water, 10 stock. So what I'm going to do is I'm just going to fill up all of these test tubes that you see on the front desk here, making solutions of known concentrations. This is going to take me about 5 to 10 minutes here, ladies and gentlemen, so if you want to speed up the video or fast forward about 10 minutes, I'm simply going to be making these solutions using my 2 volumetric pipettes. So it's going to take a little bit of time here. Feel free to fast forward or just skip ahead in the video. The first one is all stock, so I actually don't have to measure. I can pour directly in. So I'm done with all of my stock. Now time to add deionized water to all of these solutions as well. The last solution is only deionized water, so I can start by filling that up. At this point, we have made all of our solutions, and you should be able to visually see the decrease in concentration. So as we move in this direction, you can see the color becoming more faint as our solutions become less concentrated as we move in this direction. You can see all the way at the edge here, this barely has any blue with 1 milliliter of stock and 9 milliliters of deionized water. So at this point, we are ready to start taking absorbance data. Now, in order to take absorbance data, we have to use a device known as a colorimeter. as well as individual plastic pipettes. We'll explain what these are for in just a little bit. So we grab one item. So what we are going to do, ladies and gentlemen, is transfer a small amount of each solution into what I am laying on the front desk right now. What I'm laying on the front desk right now are known as cuvettes. These are small pieces of plastic that will fit inside the colorimeter, allowing us to get absorbance data. So, to start out, let me show you what this is going to look like. Okay, moving on over to this area. So you can see here, maybe not all that well, but this is what is going to be reading our absorbance. And I'm going to get the absorbance by putting a cuvette full of solution inside of the colorimeter. So you can see that the cubes fit in like this. And how does this device work? Inside of this device, there's a light that is shining through. You probably can't see the arrow, but a light is shining through, moving in this direction. If there's something interfering with that light, the light or some of the light will not make it through to the other side. Hence, that light is being absorbed. So what I'm going to do is I'm going to use plastic pipettes to fill up each cuvette with the individual solution, and we are going to jot down that data. Now, before we start out, whenever you are finding absorbance and concentration data, we need to calibrate the device. So we need to set the device saying that a specific point should have an absorbance of 0. Now, right now, the device is actually calibrated, but I want to show you this for steps moving forward, just in case we're back in school and you are actually running this type of experiment yourself. This is a type of experiment that pops up quite a bit this year. So, what am I going to do? To calibrate the device, I am going to read deionized water. So we're simply going to take our deionized water trial using a plastic pipette, and we are going to fill up the cuvette with deionized water. You don't need to fill it up all the way so it's overflowing. About 3/4 full will work. We just need to make sure that the light will go through liquid only. Now, because we are altering the concentration on purpose, if I were to use the same pipette for each solution, I would be changing these concentrations. And remember, we spent a lot of time specifically measuring out specific volumes, so we don't want to alter the concentration. So, unfortunately, it is a bit wasteful, but we are going to have to use a new plastic pipette for each solution. So, now that I have my deionized water ready to go, I'm ready to calibrate my device. The colorimeters are very sensitive. So, if you have any sort of smudgy fingerprints on your cuvette, that will impact our reading or our results. So before we put this into the device, I'm using what's known as a Kim wipe to wipe off any fingerprints that may be on the device. Now, if you were thinking logically, you'd be saying, Mr. Rice, you're holding the device with your fingers, so aren't you adding fingerprints right now? On these cuvettes, you have rigid sides and smooth sides. The smooth sides are what need to be wiped off. The rigid sides are how you hold it. And when you place this into the colorimeter, just make sure that you place the smooth side in the light detection section. There's an arrow inside of the device for you to see where that would be. So all I do here is I put in the solution into the colorimeter. I close the colorimeter. And what we need to see right now with deionized water is an absorbance reading of 0. If it's not reading 0, you simply hit the calibrate button. Now, my deionized water is reading an absorbance of 0 right now, so I don't necessarily need to calibrate, but I'm going to anyway, just to make sure that we are on the same page. So our first data point, concentration 0, absorbance 0. And that'll be true for any of these types of experiments. Okay, so now what do we need to do? We need to take the absorbance of all of our other concentrations. I'm going to start with the most concentrated solution. So that would be 10 milliliters of stock, 0 milliliters of water. This should be a 7 micromolar solution. What is the concentration going to be? Or what is the absorbance going to be? Let's find out. So we have stock solution. I'm going to wipe off any smudgy fingerprints. Now let's get an absorbance reading. I'll move this over just so you can see that it is actually reading an absorbance right now. I believe it's about 0.74. So our stock solution, we can jot down an absorbance. It's fluctuating between 0.739 and 0.740. So we'll say 0.739. So now I'm going to do the same thing with the remainder of the solutions. Now, make a prediction as the concentration goes down. What do you think is going to happen to the absorbance? Wipe off any fingerprints. Point 594. Okay. Next solution. I'm also going to move these just to indicate when they have already been used, just to make sure we're not messing up any of our data. Okay? So at this point, ladies and gentlemen, we have something that will happen from time to time during this process. We're not reading 0, 0 for deionized water, or air is not reading 0, 0. Let me double check to make sure deionized water is reading 0, 0. Okay. So the deionized water is still reading 0 on our absorbance, so we do not need to recalibrate. Let's take a look at our next solution. Point 452. 0.306. Okay, our next solution. Wipe off any fingerprints. Two. Okay. Next solution. Wipe off any smudgy fingerprints. And the last solution. Last time wiping off fingerprints. .091. So at this point, we have all of our data for part 1 of the lab. So we now have to start to analyze some of our data. If you take a look at the general format for Beer's law, which is located right here. Absorbance is equal to molar absorptivity times path length times concentration. Molar absorptivity and path length are a constant value. So if I can determine the relationship between absorbance and concentration, I can use that to help us find the relationship between molar absorptivity and path length. Watch the next video to see how graphing can help you with this process.